I wanted to start today's session by making a bit of an announcement that the channel now has one official sponsor. It's a company called Reask, and this is a company that is essentially rethinking natural hazard risk on a warming Earth by integrating AI within traditional process-based modeling. And I promise that's not just a bunch of gobbledygook. This is actually a company that I've been advising for a few years on the Earth system risk side. What does that really mean? Well, it means they're taking a look at how to better quantify how hurricanes, tropical cyclones, wildfires, and a number of other potential hazards are changing in a warming world, and also how we can predict them from year to year. So not just thinking in the long term over decades, but thinking about what we can say about the months to come. Not unrelated to some of the conversations that we often have on this channel and that I'm about to talk about today. So just wanted to thank Reask for this partnership. Again, this is a company that I have been advising for a couple of years, and so I'm pretty picky about, as you may have noticed over the years, about having any sort of commercial relationships at all. This is one of them, and so hopefully that says something about how I feel about this particular company. There is, by the way, a limited opportunity for additional sponsorships on the channel or for advertising on the Weather West blog. You may sometimes notice some ads on the Weather West blog. Over the years, I've occasionally partnered with pretty hand-chosen companies to do some advertising there. So I'm pretty picky, and the content and the style has to match the pretty low-key, non-hard sell, and generally pretty tame content in the Weather West blog. But if you're interested, or if your company might be interested, let me know and we can have a conversation. And moving forward, if you're interested, there is a link to Reask in the comment section here, and there will be additional links to Reask embedded in forthcoming live sessions. So today's topic is going to be the ongoing early season heat wave in the Western United States, and another update on what might be coming in the weeks and months to come. And also, I want to discuss at least a little bit the additional research that's been coming out, very germane to some of the conversations we've been having over the past year or so, as to why the last 12 to 18 months have been so record-shatteringly hot in a global context. There's been a lot of debate, and by debate I do genuinely mean, on the scientific side, actual real uncertainty and associated research that's coming out that's not always giving the same answer every time people run these experiments. So update on the state of the science as to why recently it has been, and no one is in doubt about this, why it has been so ridiculously record-breakingly hot in a global context recently. Again, over the same 12 to 18 month period, it is interesting that California locally has been one of the relatively global cool spots, a place where there has not been widespread record-shattering heat over the past 2 years, unlike almost every other place on Earth. There has been some unusual warmth recently, although even here, this is probably not accurately characterized as a record-shattering heat wave by any means, although it has been notable. So we'll talk about all of that in this session. So what I really wanted to start with is the ongoing heat wave, which has been significant. This is now potentially the third or fourth day in some places in the Central Valley, for example, of triple-digit heat. And although 100-degree temperatures are not rare by any means in most of the Central Valley, it is somewhat unusual to get multiple triple-digit days this early in the season. Keep in mind this has all occurred in the first week in June, so this is still pretty early in the season. If this was mid-July or August, these temperatures would be somewhat less remarkable, but it it is not August, it is June, and so this is a significant heat wave. Perhaps more notable, though, is the very warm temperatures we're seeing at higher elevations. So if we go up into the Sierra Nevada and up into the northern mountains, so up by Shasta and including places in the north like Mount Shasta City, we go south and east to Truckee and Tahoe and Reno. Seeing temperatures in the mid to upper 90s at that elevation at this time of year is highly unusual. And we've also been seeing significant heat in the desert southwest. Again, this is a hot place and this is a pretty hot time of year, but even there have been some records broken. Death Valley, for example, broke its daily record yesterday, 121 degrees Fahrenheit. 120 is, again, not rare in Death Valley in general, but they are unusual this early in the season. So Las Vegas, too, the city of Las Vegas, approaching or exceeding its earliest 110 or 112 degree day. I don't know exactly where the mercury fell yesterday, but these are the kinds of temperatures we're talking about. These are temperatures that are not earth-shattering for peak season, but are nonetheless highly unusual for this early in the season across a pretty broad region. Now, down in northern and central Mexico, of course, as we've been talking about, the temperatures that have been occurring there are actually record-shattering for any time of year. So the heat wave down in Mexico that continues now is still remarkable and extraordinary to a much greater degree than it is, say, in California or the Western U.S. right now. But it's the other piece of this is, of course, that this is a very widespread heat wave extending all the way from central Mexico in the south up into British Columbia. So all the way from central Mexico to southwestern Canada across the interior. One place where it is not extremely hot, though, is along the Pacific coast. So if you look at the beaches all the way from Baja California up to British Columbia, it's not remarkably hot. There have been some warmer days when the marine layer has been a little bit less persistent, but already that marine layer has returned with a traditional June vengeance, if you will. Early June gloom is not unusual this time of year, and that's particularly true this year because the near-shore ocean temperatures have cooled considerably. Because again, along the west coast of the United States, the overriding factor in how warm the near-shore ocean is the extent of, or the magnitude of, the upwelling, the vertical movement of cooler water from lower levels of the ocean up to the surface. This can completely override even a very warm overlying atmosphere, and indeed that is what we're seeing right now. With relatively decent northwesterly winds, which again induce that upwelling along the west coast, particularly along the northern California coast, where ocean temperatures are near to below average for this time of year. That's in great contrast to the air mass across inland areas. You only need to go inland about 20 or 30 miles to have an air mass that's much warmer than usual, so there is an unusually high contrast between the cool ocean areas and the warm inland areas. That is, of course, the usual setup. That is the reason why California gets its famous sea breezes in the San Francisco Bay Area and the LA area, and sometimes extending into the Central Valley through the Carquinez Strait into the Bay Delta region in the southern Sacramento and northern San Joaquin valleys. That gradient, though, is kind of supercharged right now, so there could be some very robust sea breezes as very hot temperatures continue across well inland areas, but near to below average conditions prevail along the coast with that near shore cooling and that upwelling and deep marine layer. I wouldn't be too surprised, given some of the seasonal outlook, if this pattern persisted for most of the summer, where most of the land area of California is exceptionally hot across inland areas, but near the coast, temperatures are near, even occasionally below average due to a very persistent marine layer and strong upwelling, keeping those near-shore ocean temperatures cool. This is a pattern that we've seen repeatedly in some recent summers that ended up being very hot on a statewide basis, but a lot of folks in coastal Southern California and the Bay Area were sort of left scratching their heads and saying, what heat waves? I think that may be a prevailing story again for much of this season as well, especially with the most recent update of the seasonal predictions coming out that are strongly indicating that this kind of pattern may persist pretty much all of the summer. It may break down a little bit in the fall as that nearshore upwelling and cool temperatures in marine layer, as it usually does, fades, and there's less of a gradient between hot inland areas and cooler coast. So I think late summer, early fall is still when I would expect the nearshore areas to have their highest chance of significant heat waves this year. But overall, I think this may be a pattern where this may be a pattern where the inland areas just stay very toasty for most of the summer, which is a slightly different estimate from what I had been saying earlier in the spring, where I thought it might take till August or September for the inland areas to become hot. Now that seems to be the pattern that's established itself already and may persist for much of the rest of summer. That said, the coastal strip in California within 20 or 30 miles of the coast, where most of California's population lives, may be in a very different situation. For much of the summer, it doesn't mean there won't be transient heat waves, and it doesn't mean that the fall won't become very hot just about everywhere, but right now that's sort of what it looks like. So this current heat wave looks like there's going to be a bit of a temporary reprieve going into the weekend for some areas that are within reach of the sea breeze. So this, of course, includes the Bay Area, coastal Southern California, the North Coast, and also parts of the southern Sacramento, northern San Joaquin Valley, where you can get that delta breeze. It may resurge a little bit, though, by early next week as that ridge re-strengthens. And across inland areas and higher elevations of northern California, the Sierra Nevada, the Shasta Mountains, Reno, Tahoe, those places are just going to stay really hot. There may be a slight drop over the weekend to merely above average temperatures, but then it's going to get genuinely hot again by early next week, with a lot of triple digits persisting at least through the middle of next week in those areas and perhaps beyond. It looks like it could be still a fairly prolonged heat event, another 7 to 10 days of this across the higher elevations and the inland areas of California. Again, near the coast, this will be a different story. The even more anomalous heat will really be centered, though, more across the Great Basin. So we're talking about Nevada and Utah, and into the portions of the interior of the Pacific Northwest. This is a part of the country where often there is less wildfire activity, like the Great Basin, for example, simply because, for the most part, there is less vegetation in the Great Basin. Now, that's not to say by any means it's a barren desert. Most deserts are actually not barren at all, but in particular, the Great Basin has pockets at the higher elevations of significant contiguous forest up in the mountains. It's called the Basin and Range region for a reason. The ranges intercept more moisture and have more vegetation and tend to have some forested locations. But my point is that at lower elevations in the Great Basin, there's a lot of variability in how much vegetation grows from year to year. There is essentially the perennial vegetation, the sagebrush, and this very dry desert environment tolerant vegetation, this native vegetation, that tends to be spatially discontinuous. So you have clusters of sagebrush or other scrubland that sort of clusters in small areas, usually less than an acre in size, with gaps in between where there's little or no substantial vegetation. The challenge is in this region, and this varies depending on where you are in the Great Basin, but it is a large problem overall, is that there's been an influx of invasive grasses, and these tend to fill in the gaps between these discontinuous clumps of native vegetation at lower elevations in the Great Basin. And the challenge here is that following wet years, and we now have 2 wet years in a row across much of the Great Basin, there's a huge proliferation of grass. So now that conditions are drying out rapidly, are becoming extremely dry in a place where there is not always contiguous vegetations in a spatial sense, but there certainly is in many regions this year where that wouldn't have been the case during the peak of the 2010s drought, let's just say. Now there is potentially a continuous fuel bed for grass and brush fires. So I would expect to see this summer some very large grass and brush fires in the Great Basin, in places where in some years there simply isn't enough contiguous vegetation to support large fires, because often the ignitions would kind of sputter out. Lightning might strike a cluster of of sagebrush or an isolated patch of trees and burn itself out pretty quickly over a few acres. But right now, there's so much additional moisture in these regions that and you combine that with the influx of invasive grasses, and there's a higher potential for large wildfires in the true lower desert regions or the upper desert regions all the way from southeastern California into the Great Basin this year, especially given that we also expect this summer to continue to be anomalously hot and in the Great Basin anomalously dry. So the summer monsoon in that part of the country may be weaker than usual, and that could also present some challenges there. So I wouldn't be surprised to see some significant wildfires potentially popping up in parts of the deserts and Great Basin that don't always see that level of activity in each year. So one consideration there. And there's been a lot of conversation about, because this occurred earlier this week, I guess it was less than a week ago, feels like a bit of a whirlwind, but there was a significant grass fire in the eastern San Francisco Bay Area, the Corral fire, which burned, I believe it was primarily east of the National Lab, near Livermore, and burned all the way up. Essentially, it crossed 580 and burned all the way up to oh gosh, it's not I-5. I'm missing which interstate it is on the east side of the west side of the valley and the east side of the hills there. My apologies. In any case, it was a true grass fire. The fuel type was like greater than 99%. Those golden hills that are so iconic for Northern California. Also, in many cases, invasive grasses, by the way, but from a much earlier period. Something that I think some folks aren't aware of. But anyway, this was a significant grass fire. It burned over 10,000 acres. I think it ended up being closer to 15,000 acres, which is not too surprising because grass fires can get really big really fast. The grass is known as a flashy fuel. That's because it can become quite volatile quite quickly. So you don't need a prolonged drought to really dry out grass. You just need, in some cases, 8 to 12 really dry or windy hours. And in this case, what we had was dry enough conditions, but quite windy conditions. There was a strong sort of west to east wind, not unrelated to that strong coastal gradient, by the way, that I mentioned between the really hot valley and the cool coast. Gusting over 40 miles an hour drove that grass fire pretty hard eastward and caused it to jump roads. There was one inhabited structure unfortunately destroyed, but in the end, this was some folks, and I spoke to a number of folks in the media about this fire, and they were sort of wanting to talk about it as this catastrophe. I don't think this is a good example of a catastrophic wildfire in California, although it was fairly large, at about 15,000 acres, and fairly early, burning in very beginning of June. Again, early season grass fires are exactly the kind of fires that you would expect to see in a geographic region like California with the ecosystems that we have. The grass is what dries out first, and this fire, but for those winds, would have been quite unremarkable. Now, given that it was windy, it was a lot more remarkable, and there were evacuations and road closures. By the way, the comments, that was Interstate 580 that I was mentioning earlier. Thanks for that. But the key here is that grass fires in the early season are not unusual. It is usually the first kind of wildfires that we start to see emerging because that's the kind of vegetation that dries out first. And they're also usually the least threatening kind of fires. Not always. This is not always true. There are always exceptions, particularly when the winds are very high, like they were. But generally speaking, you do not get nearly as much energy from combustion of grass as you might from a higher intensity forest fire, or even a higher intensity brush fire in the Chaparral in Southern California or something. There simply is less potential thermal energy per acre of vegetation in a pure grassland than there would be in a mature forest that was burning at a high intensity. Now, it's also true that if you have a ground fire in the forest, so something that does not get up into the tree canopy in a well-managed or healthy forest ecosystem, you also don't see high-intensity fire. That is one of the main benefits of prescribed burning, which there's been a fair bit of this year in California, more than there had been in recent years, which is good news. But what I really wanted to emphasize is that although this was a notably large fire, it was a grass fire, so it was not as high intensity as a fire burning a different kind of vegetation would be, and I don't think we would have seen as large a fire had this been an ignition in the forest, for example, because the forests just aren't that dry yet in California, even following this heat. I do think we'll start to see more and more fires. Things are drying out, but things are not at this point exceptionally dry because we've had 2 wet years. And until this point, it hasn't been exceptionally warm across most of California. Now that's starting to change, and as I've mentioned, I think that this fire season is going to shift from a pretty low gear at present to a very high gear by late in the season. So I do actually think that this year will be a lot more active than the previous couple of years for regions I've discussed previously. However, I think that the Corral fire in particular is not a great example of extreme wildfire hazard in California. It's really just a testament, I think, to 2 things that are interesting. One is that increasingly there are subdivisions that encroach on fire risk areas. Some of the places that were at risk from this fire on the west side of 580, thank you. Those subdivisions did not necessarily exist a couple of decades ago, and so previous grass fires, and pretty much this whole area burns every 5 or 10 years. That's the nature of grasslands, is that they tend to burn with higher frequency and lower intensity than forests, generally speaking. They simply weren't there previously to be at risk, and so some of the reason why there was more concern over risk to houses and property was because, well, there are more houses and properties potentially in this footprint than there used to be. So that is a sort of a perennial challenge. And the other thing is that this fire, we don't always see 15,000 acre grass fires in this region at this time of year. Part of that was because of the windiness and the location. It was right in that wind tunnel downwind of the Altamont Pass where the wind farm is. There's a reason why that wind farm is there. But also, there is a really high level of fuel loading of the fine fuels this year. So in other words, this is what I was talking about in the Great Basin. There's been a lot of extra growth of grass and brush. Not just in the Great Basin, but also throughout California these past 2 wet and cool years. This has been a very good couple of years for growing vegetation. So the good news is the forests, I think, have gotten a couple of years to recover from the historic droughts of the 2010s. That's good for them. But it also means that the grasslands and a lot of the seasonal and perennial brush has really gone gangbusters in the last couple of years. At the same time, where there's been a lot less wildfire activity than previous years. So you both have a lot more vegetation growth and less recent fire activity to remove some of that growth. So what does that mean? As I've mentioned before, is that when there are fires this year, they're going to have a lot of additional fine fuels to potentially combust. So more grass and more brush in a lot of regions. That could lead to a heightened level of grass fire activity because they will, although they're still going to be burning at a lower intensity than a forest conflagration, generally speaking, there is also going to be more thermal energy available to grass and brush fires than would be the case during a drought period because there is literally more carbon biomass available to combust. So that's one reality I think that we're going to see this fire season is we're going to see a pretty rapid uptick in grass and brush fires, which tend to be under most conditions, unless there's extremely windy conditions or high competition for firefighting resources due to a lot of other fires co-occurring. They tend to be manageable because you can essentially engage in more direct firefighting activities in non-wind-driven grass fires. If the winds are not high and it is truly a grass fire, often fire crews can approach it, pretty directly rather than going as it's said indirect. In cases where topography is very challenging or fire conditions would put crews at unacceptable risk, which is often the case in complex topography or with fires burning in other vegetation types under drier conditions. So grass and brush fires, they can certainly pose a threat, especially if it's especially dry and windy. But generally, they're a bit of a different beast than some of the larger fires burning in a mix of vegetation types. And that's particularly true when it's a grass fire burning only grass in an area encircled by essentially interstate highways between 2 significant population centers and with a lot of access to firefighting resources. So one lesson is not that it's exceptionally dry right now, since it's not, but that it could become much drier and even drier than average by later in the season. But the more interesting thing is that there's a really high level of fine fuel loading this year. So a lot of grass, a lot of extra brush, and that a lot of that may dry out by later this season. So it is a little bit of a warning sign with respect to that, I think. And also that there may be sort of an interesting risk corridor this year along in the East Bay Hills and sort of along this corridor about 15 to 30 miles inland from, or maybe 20 to 40 miles inland, something like that, from the ocean, depending on where you are, with the coast ranges, with this strong thermal contrast between the cool coast and the very hot inland area, with that enhanced gradient relative to most years likely to persist the rest of the summer. We may see some more of these days where there's a really strong west to east winds, 30, 40, 45 mile an hour gusts even, in these sort of these grasslands or these scrublands on the eastern slopes of the coastal mountains. So that may be a hot spot of fire activity for much of the summer, because we will have the combination of potentially strong gusty winds, but also quite hot temperatures, since you tend to have more of the temperature influence from the Central Valley on that side of things. So there's maybe that strip on the eastern slope of the coastal mountains is something I hadn't quite identified until thinking about it in the wake of the Corral fire. That could be a risk hotspot this year because of the combination of very strong sea breezes due to that thermal contrast. So not dry offshore winds, but actually moderately moist onshore winds that are nonetheless hot enough to potentially fan those flames in places where there has been a lot of extra growth of grass and brush this year. So a little bit different than the kind of risk hotspot that we've sometimes talked about in the past, but it's something that occurs to me this week thinking about what reflecting on the Corral fire. And of course, that could become a little bit more challenging later in the season. With the Corral fire, there was almost unlimited resources available because there's nothing else burning in California right now. Later in the season, that might not be the case, and so that resource availability may come into play a little more strongly as we get into that part of the season. So that's essentially what I've got to say about the ongoing heat wave. It does look, by the way, in the ensembles, pretty likely according to current model ensemble predictions, that this heat wave will finally fade by mid-June. So I don't think this is going to last all month. I do think we've got another 7 to 10 days of it across the interior of California and the higher elevations of California, as well as the Great Basin. But it does look like things will sort of equilibrate closer to average mid-June temperatures by around then. So I don't think this is necessarily going to get worse before it gets better. I think it just might persist until it finally fades by mid-June. And I'm going to take a pause right now. I might actually do questions in 2 phases today. So first, I'm going to take a look at the questions that come in on the sidebar regarding everything I've talked about so far. So the current heat wave, what it might do next, the outlook for the rest of the summer and fall, and also thoughts about the wildfire season in the context of the nuances and the recent Corral fire that I was just talking about. Then I'm gonna pause the comments again. While I won't pause it, you can continue to add it, but I won't be looking at it. And then I wanted to discuss also the recent research and the new evidence that's coming out regarding essentially how the discussions surrounding why the Earth has been so incomprehensibly warm over the past 12 to 18 months, and why that is, and what that may or may not tell us about our understanding of the situation at large. So again, taking questions right now about the first half, and then in the second half, I'm going to have another brief monologue, and then we can have a discussion on that topic in a moment. So I'm going to wait a few moments for some questions to come in, because I know there's a lag between what I'm talking about and what comes up on the screen. By the way, hopefully, I know some folks have mentioned that the closed captioning has not been available on some of these sessions. I apologize for that. My intent was to have it available during all of these. It should be available during this one. I did make sure. Please do let me know if for any reason it becomes unavailable. I think it's always available in the recorded version afterward, but sometimes the live auto captioning, it defaults to turning itself off for some reason, and so just remind me if that's ever an issue. So I'm going to start, there's a few questions coming in. I'll start answering them now. Let's see. Andrew asks, in the 1970s, the East Bay spring meant deep blue skies, puffy cumulus clouds in the afternoon, and fresh air and crisp ridgelines. Now winter rains are followed immediately by haze and smog. Climate change? Well, that's actually a difficult question to answer. One of the interesting things about air pollution in the United States is it actually peaked, believe it or not, in the 1970s. It's actually been, with the major exception of wildfire smoke, which has gotten a lot worse since the 1970s, virtually all other sources of pollution in the U.S. have substantially decreased since the passing of the Clean Air Act decades ago. That was a pretty major environmental policy success in that it really did achieve rapid and sustained declines in most forms of major air pollution in the U.S. California's decline has been even more dramatic, especially in places like the LA basin. There may be some specific regions where this has changed a bit, but this is kind of interesting to just juxtapose because haze doesn't always mean air pollution. If you're within range of the influence of the sea breeze from the ocean, for example, or the bay breeze, as it might be in certain parts of the Bay Area, some of that haze is actually coming from natural aerosols in the atmosphere. So essentially sea salt. Sometimes that's a combination of sodium chloride, so literally table salt, and magnesium chloride. And so, these fine salt particles can result in some degree of haze that is not really harmful pollution. Now, sometimes that can mix with harmful pollution to create more prevalent smog or to serve as cloud condensation nuclei for the marine layer. So it's a little bit difficult to say whether that haze is actually even air pollution, or in some cases it might actually be sea salt brought in on the sea breeze. It is true that there is major challenges still with air pollution in California, particularly in the southern San Joaquin Valley. That is one place where air pollution remains severely bad for much of the summer, and it actually represents a major public health threat. This is often worse during the drought years, and climate change probably is making it worse because we're getting hotter and hotter temperatures that are and essentially more and more, you could call them profound heat domes in summer that's keeping a lid on the air in the San Joaquin Valley and trapping those pollutants. Some of it is just dust from barren agricultural fields during droughts. Some of it is smog, photochemical pollution from tailpipe emissions and oil and gas leakage from wells in the San Joaquin Valley, combined with a lot of sunlight and high temperatures. That can be a pretty toxic soup of air, and that does sometimes spill over into the East Bay, depending on where the winds are coming from. So I think, in my mind, there really are actually two regions in California, arguably somewhat forgotten regions, at least by national news standards in California, where the air pollution has either not dramatically improved or perhaps has even gotten worse. And that is, as I mentioned, the southern San Joaquin Valley and also the Imperial Valley. So far southern California, east of the coastal mountains in San Diego County, the Imperial Valley and the Salton Sea region has, in some cases, really terrible air quality that has gotten significantly worse as the Salton Sea has shrunk over the years, and as some of the deposits that were formerly at the bottom of the Salton Sea are becoming aerosolized when it gets windy, dry, and hot. This is also a super hot part of the state. In fact, it's arguably the hottest populated part of California. Death Valley gets hotter, but very few, if any, people permanently reside there. But there are communities in the Imperial Valley that regularly see temperatures of 115 degrees or hotter in summer. And if you combine that with the fact that sometimes it's not a dry heat, but in fact a humid heat, and that there's a lot of air pollution, that results in major public health impacts there. So I think the East Bay is an interesting example where objectively I think overall pollution in the air has decreased since the 1970s, but there may be periods where you actually get some of that pollution from the San Joaquin Valley sort of coming from the south and east and maybe infiltrating from that direction. And so just an example of how air pollution, even though sometimes you can pinpoint it to point sources, actually spreads quite widely and can affect people well outside of the region where it's being produced. So that's me just talking about some related things. I don't have a specific answer to your question, but I kind of suspect that that's the dueling dynamic. In the East Bay, some of it could be actual just haze from sea salt mixing with some of the pollution from the Central Valley. Blue skies in Humboldt County today, which is somewhat remarkable. I guess it depends how close you are to the coast, which is often socked in with the marine layer this time of year. But if you're inland, that's a little bit less unusual in June, but nonetheless an indication that there is strong ridging aloft. Question from Damien: did the fast jet stream fuel stronger storms recently? Okay. Let's table this one and come back to it in a future session about climate change, since it's a little bit distant from the topic today. And it's also a very complicated answer that I probably don't have time for in the 20 minutes we've got left today. But it's a good question, and please do feel free to ask it again, either in one of the Ask Me Anything sessions that'll be coming up, or in something that's kind of specifically related to climate change and storms. Both of those will be upcoming. Monique mentions hot and blue skies here in Shingle Springs near Placerville. That's consistent. That's in that elevation band where this heat wave is perhaps most intense in California, because it is pretty unusual to have sustained temperatures well into the 90s at that elevation this early in the season. Another remark from Mark, different from other folks in that there is the Delta breeze early this morning in Brentwood, so that's an indication that this temporary reprieve and sort of a progress inland of the marine layer and that sea breeze appears to be materializing. A question from Puma Mountain Lion 777: since oceans are warming, will that ever affect the upwelling ocean temperatures, the upwelling that I mentioned earlier, which was keeping the coast probably a lot cooler than would be the case otherwise this summer, maybe even cooler than the recent average, or will those always be relatively cool regardless of global warming? That's a really good question, and there is evidence that with a sufficient amount of warming, it's not totally clear exactly what that means, so I'm leaving it deliberately vague, that we would see a decrease in the amount of upwelling off the coast of California. Now, this has less to do with the amount of warming itself and more to do with atmospheric circulation changes. So it's actually the prevailing northwesterly winds, so essentially parallel to the coast, that actually induce a net movement of water perpendicular to the coast. So directly from northeast to southwest, so water, if this is the California coastline, water moving away from the coastline due to winds that are blowing from this direction. And I'm realizing that folks are going to be seeing this in mirror image, but you get the same sense of it on the camera. But the reason I mention this is that it's really a question of what happens to those northwesterly prevailing winds and the associated, it's called Ekman transport, that perpendicular flow of water along the coast that encourages to conserve mass. Water has to come from somewhere to fill the void, and so it comes up from underneath, because it can't come from the east because that's where the land is. And so it induces this vertical circulation in the nearshore ocean that's actually driven by northwesterly winds parallel to the California coast. That's a product of the prevailing subtropical high pressure system offshore. So you have in a map view, my previous hand motions were in a vertical sense, but now we're in a horizontal sense. We have that circulation around the high pressure system. How strong that Pacific high is in summer, in spring and summer, I guess, dictates just how strong that northwesterly flow is, and there's some indication that it may weaken slightly with significant warming. However, That's not totally certain, and even if it happens, there's still going to be net upwelling. It might just be slightly weaker. So in general, the California coast, at least when you don't have offshore flow conditions, so all bets are off when you lose the marine layer and you actually have offshore flow from east to west. That's why it's possible, for example, for downtown San Francisco to get to 106 degrees, as it did a few years back on a major offshore wind day. But most of the time, you're still going to have that strong, relatively strong coastal upwelling, which leads to an interesting question about what happens to that temperature gradient in a warming climate. And there's still some uncertainty. And I've seen some news articles that perhaps are a little bit making some bold statements that are not yet. You might hear Luna here again. A little bit bolder than the scientific evidence necessarily supports at this point regarding what happens to the marine layer in California, because there's really two competing factors. One is clearly it's getting warmer everywhere, both inland and at the coast. But there's a pretty strong indication that it's going to get warmer faster in inland areas. And if that happens, it's actually going to increase the already pronounced gradient between the cool coast and hot inland areas. And that, overall, with global warming, there's a suppressing effect on the marine layer, which would result in less coastal cloudiness and warmer coastal conditions. But locally, to the extent that the inland areas warm faster than the coast, you might actually see an accelerated sea breeze, an increased contrast between coastal and inland areas, and that could actually drive, in some ways, a stronger sea breeze circulation and perhaps a more robust marine layer. So you can see how these factors might counteract each other, and we honestly don't know exactly how they might shape out. There's been some modeling work that points in both directions. Which of those factors win out? Do we see more suppression from the top down of the marine layer and things get warmer at the coast? Or do we see a stronger, more robust sea breeze as that thermal gradient between the coast and inland areas increases? That would tend to result in, it wouldn't affect inland areas so much, but it might keep the coast pretty cool by even cranking up nature's air conditioner to an even greater degree than is usually the case. We don't know quite how that's going to pan out, and it really could go either way. So stay tuned. There's probably going to be some future modeling work on that, but you can kind of see how if the latter is true and we really crank up that marine layer strength, the kind of prediction that we're having for this summer would be very much reminiscent of a future where the coast warms a little bit, but not as fast as inland areas. The inland areas warm very rapidly, and we actually get this increasingly strong sea breeze circulation as a result of that thermal gradient increasing. But the reality is we don't know quite how that might play out, and it also might play out very differently in summer versus fall. So in the summer we have that coastal upwelling, as I mentioned. In the autumn, that upwelling tends to weaken anyway, and so in a warming climate maybe we might actually see accelerated warming in coastal areas in autumn. And that's sort of what we've seen in recent years, because we lose that nature's air conditioner in the fall, and then we actually might see warming rates in autumn that are more even between inland and coastal areas. That's just sort of an observation on my part there. Question from Mary. With the persistent heat in the Central Valley, any risk of drought returning this summer? Is there a wildfire risk for California outside of grass fires? Well, I've sort of addressed the latter point. Yes, especially later in the summer, I think we are going to see a return of much more active wildfire conditions, not just in the grasslands, but also in other areas, including maybe by the end of summer, even the higher elevations, although I think it'll take longer since there's still a lot of extra soil moisture and even some lingering snowpack at the highest elevations. But the question of drought is an interesting one. Will there be a water supply deficit from the perspective of urban areas? Essentially, I can guarantee you that won't happen in calendar year 2024. The water supplies are just in too good of shape right now from a reservoir perspective for that to happen this year. Agriculturally speaking, there's a lot of water politics involved in terms of water allocations, but generally speaking, the only reason why there might not be full water allocations is concern about a potential drought developing in future years, but I don't think we're going to see dire levels of agricultural water allocation either, because right now, again, reservoir levels are reasonably good. They're higher than they've been in a number of years, in fact. The question about, though, sort of meteorological drought or hydrological or ecosystem drought, so ecophysiological drought, is perhaps a different issue. We certainly don't have any significant drought conditions right now anywhere in California, but that actually could change by this upcoming fall and winter. If we do have an especially hot and dry summer across inland areas and a dry fall, I would expect mild to perhaps moderate drought conditions to be painted on that drought monitor map potentially by mid to late fall again. So I would be somewhat surprised if we had any kind of severe or worse drought in California by the fall, but we are going to see that quote unquote abnormally dry contour, I think, creep into the interior of California and maybe continue to spread westward and intensify fall into winter. This is somewhat dependent on what happens this coming winter, but right now I'm definitely leaning towards a warmer and drier than average winter next year, so that may be more of a problem for 2025. Where I do think these impacts might manifest themselves by late in this season is with respect to wildfire. Water supply wise, I think California is going to be just fine this year. Late season, though, things really may dry out enough that it starts to really amp up the wildfire activity, especially given all the recent growth of extra grass and brush. Ron asked a good question. Why does the cool water upwelling of the nearshore ocean dissipate to a certain extent in the autumn? The short answer for that is because it's driven by this northeastern Pacific subtropical high. The northeastern Pacific subtropical high weakens and becomes suppressed in fall as winter starts to approach, and so essentially the atmospheric circulation feature that drives that upwelling is either no longer present or it's much weaker. And so you just don't have that mechanism driving that northwesterly wind, and so you lose to a great extent that upwelling. In some years more than others, but on average in fall it's a lot weaker than summer, and that's why you tend to see the hottest days of the year in places like San Francisco often occur in September or October for that reason. It's not because the sun's intensity is strongest in September or October, of course, but it's because you lose that air conditioning effect much of the time from that cool upwelling. All right, so I think given that we've only got a little bit of time left, I did want to talk about one other thing and ask some additional questions. So I'm going to table the rest of the questions for now and talk a little bit. I can make this relatively brief. You may recall that I've been talking periodically every 5 or 6 sessions or so, giving an update on the global temperature anomaly, and unfortunately, the numbers for May are now out, and it looks like May was yet again another record warm month, exceeding even May of last year, which is a pretty high bar, actually, so that is eyebrow raising. The margin by which we're breaking records is starting to slow, so it's at least somewhat likely that perhaps June will be the first non-record breaking month in over a year. That's not saying a lot because the previous record was set just a year ago, so we're really just leveling down to last year's levels. Hopefully by later this year we drop a little bit further. But the bigger question is, why have we been so darn hot, so record-breakingly hot? By certain data sets, last year was the first 12, included, the 12 months through May of this year may have been one of the first 12-month periods in excess of 1.5 degrees centigrade above the 20th, or the pre-industrial average, excuse me. Again, just to clarify, this is different than reaching the IPCC 1.5 degree target, because that is defined as being the first decade where temperatures are on average above 1.5 C. We are not there yet. If we look at the decadal average, we've seen maybe 1.3, 1.35 centigrade of warming, although of course all of the hottest years are the last few years. So as we start to lose the earlier years in that moving average, that we're going to get closer and closer to 1.5 in the 10-year mean. But the interesting question is, why has there been such a jump? Because 2023, 2024 has been a lot hotter than was 2021, 2022 by as much as about 0.3 C, which is a big deal if the entire anomaly between over a century ago and today is about 1.3 C, and then suddenly we jump by another 0.3 over just a couple of years. That's a pretty big number. So what's going on? Well, one thing I would reiterate once again is that the main reason why we are seeing temperatures near or above 1.5 C, at least on short time scales, is essentially, well, it's global warming. If you imagine, if the warming we've seen so far, the linear trend gets us to 1.3, 1.35 out of 1.5 to 1.6, that's clearly most of your answer. Human-caused global warming is like 80% or more of why we have been as hot as we have been. But human emission of greenhouse gases didn't suddenly spike in 2023 in a way that would explain why suddenly temperatures jumped up by about 0.3 C additional to that long-term trend. So what's going on there? So to explain the spike over the last year or so, I think we have to look at different things. Of course, global warming to date is the elevator that got us most of the way there, but then the last few floors, how did we get there? One piece of it, a significant piece of it, is the transition from a persistent La Nina-like state to a strong El Nino last year, which probably resulted in a global increase in temperature over the course of about a year of at least 0.1 degrees centigrade and maybe up to 0.2, although probably closer to 0.1. So of that extra 0.3 jump, the transition from La Nina to El Nino probably explains at least a third of it, maybe more like half of it. So that's a pretty significant chunk of the difference. So if we think about the human-caused warming that gets us to 1.3, 1.35, and we think about the natural variability, the La Nina to El Nino transition gets us another 0.1 or so degrees. Now we're like 85 to 90% of the way to explaining the full value. But that still leaves a substantial amount, 0.1 to 0.2 degrees centigrade of what happened over the past couple of years. And the most likely answer there is not so clear. This is where it's a little bit less obvious what's happening. So even though we can readily explain 80 to 90% of the anomaly and virtually 100% of the long-term trend up through 2022, it does still look like something interesting might have happened over the past year or so. And I mean interesting both intellectually and somewhat euphemistically, in the sense that interesting could be random variability and therefore not particularly good nor bad, or it could be something that perhaps maybe something we're missing with global warming, which would actually be a little bit more concerning. I don't think it's fully clear which of these it is yet, but there has been a cluster of recent studies focused on two topics that have been hypothesized as playing a role in this temperature spike. One is the 2020, I believe it was the 2022, early 2022 eruption of the Hunga Tonga volcano in the South Pacific near Tonga. And that was an exceptional eruption, and then it was a very large explosive eruption that put an undersea eruption that vaporized a very large amount of seawater, and in the eruptive plume injected it all the way into the stratosphere, above 50, 60,000 feet, even up to close to 100,000 feet in the air. Extremely high levels of water vapor injected into the stratosphere. This probably did have regional climate effects in 2022, certainly in the southern hemisphere. In fact, there's pretty strong evidence that affected the rainy season in Australia. But even the research team that found that relatively large regional effect found that the global effect in terms of the planetary warming was essentially negligible. Teams have actually found that the effect of this volcano was probably plus minus hundredths of a degree centigrade. And so some teams have suggested there may have even been a weak cooling effect from the aerosols counterbalancing the weak warming effect from the extra water vapor in the stratosphere. In other words, at this point, there's no real evidence that this was a substantial factor in this temperature spike. We're talking at most hundredths of a degree centigrade and maybe even less than that. So at this point, unless there is additional research that comes to a very different conclusion, I don't think it's likely that that played a meaningful role in what happened between 2022 and present. There's another piece, though, that I think there is a stronger argument that it may have played at least a detectable role, and perhaps a slightly larger one than that, which is this relatively rapid phase-out of polluting aerosol fuels from ocean-going cargo ships. This is the sulfur aerosol reduction, the IMO 2020 regulations that went into effect relatively rapidly reduced the amount of aerosol pollution coming out of ocean-going cargo ships. Turns out there's a whole lot of ocean-going cargo ships, and so this potentially at least could exert a global influence that is not negligible. Very likely larger than whatever the effect of that volcano was, at least. I think that's fair to say at this point. How large is it? There's a number of studies. In fact, that there's about to be a special issue of the Nature of a bunch of different papers that are looking at this from different angles, because this is of considerable interest and uncertainty. Some research groups are suggesting that this was a pretty substantial factor and could potentially have contributed as much as 0.1 centigrade or so of warming over the past couple of years. Given that that's roughly comparable to the magnitude of the transition from La Nina to El Nino, that's not insubstantial if the higher end estimates end up being right. There are other research groups, though, that suggest that the real effect is actually quite a bit lower, maybe on the order of hundredths of a degree Fahrenheit. So there is generally now broad agreement that the net effect of IMO 2020 regulations is a warming influence, although it is small by anyone's estimate, but maybe not very small. It may be modest, but certainly not negligible, because on the low end, the estimates of the influence over the past couple of years are on the positive hundredths of a degree centigrade, so that's on the low end. That might not explain very much. On the upper end of the estimates, closer to 0.1 centigrade or a little bit higher, that would explain at least a piece of this temperature spike. So this is an interesting topic of research. There has been some pushback to the higher end estimates because there's a sense that while the long-term response might be as much as 0.1 centigrade or so, it might take a decade or more to fully experience that warming from this emissions change. So the effect between the last couple of years might be much smaller, on the order of just a few hundredths. So it remains to be seen, honestly, just how substantial an influence this was. But I do want to emphasize that this is not resulting in some huge spike or a large fraction of what we've seen over the, in terms of the total warming. So keep in mind, we're talking about 1.5, 1.6 degree anomaly above the pre-industrial average for the last 12 months or so, depending on the data set. On the high end, these IMO shifts in the sulfur aerosol emissions from ships could have contributed up to about 0.1 C on the high end, in which case it's still a quite small fraction of the total, but not a negligible fraction. If it's closer to the low hundredths, then that might be even smaller. Either way, though, it is something to be thinking about, because there's going to be further aerosol declines in the next decade or so, not just from ships, but from lots of other sources. And so overall, that aerosol unmasking effect is not negligible. It will play a role in why the warming over the next decade or so is likely to be faster than the warming we've seen for most of the last 30 or 40 years. So that's an important consideration in and of itself. This is science in action. There's genuine uncertainty, and we'll see what this shakes out to be. But unlike the volcanic eruption, which is probably plus minus zero if you include the uncertainty bars, the effect of the aerosol policy changes is likely not zero. It is at least a very slight warming, perhaps more like a modest warming that's not quite so slight. So this is just another piece to the puzzle. It's not the main answer, but it is something that is interesting and could be contributing at least slightly to this recent warming spike. And the slightly more important piece of this is that won't go away. So if this was just some natural blip, eventually things would reset themselves in a few years in all likelihood. But this emission change from the shipping policies, that's going to persist. If whatever the effect is, we're going to retain it moving forward. So that's one thing important to recognize. And the other piece of that complexity that I would mention is that the global effect might be quite small, although it is possible that regionally the effect is actually notably larger, because most of global shipping occurs in relatively concentrated shipping lanes, and mostly in the northern hemisphere. So there are regions where this aerosol decrease might actually be more concentrated, and it actually might explain a larger fraction of the regionalized warming across some of the northern hemisphere ocean basins, the North Atlantic and the North Pacific, Indian Ocean in particular. So Could this explain some of the anomalous ocean warmth to a slightly greater extent? So not very small, but maybe a little bit larger of an explanation. I don't think we can rule that out at this point. So while the global effect is likely positive, though ranges from very small to small, the regional effect may be more like small to locally a moderate effect. And I'm being, again, deliberately vague here because we don't have the numbers on this yet, but that's sort of my read of a lot of different and sometimes conflicting research that's coming out on this at the moment. I don't think this is an overwhelming effect, but it is probably present. That's sort of what we can say right now. So I think that's probably the end of my monologue piece on that. We're at the hour, but I did want to take the opportunity to ask questions specifically related to the recent warming spike globally and its potential causes or not. So I did want to take an opportunity to ask. I know there's a bit of a lag between when folks are hearing me speak and when I'm actually speaking, so I will leave. I'm deliberately leaving a little bit of wiggle room in my monologue here so that people have time to upload whatever questions they want in the live comment section. By the way, there is a couple of folks who have mentioned my new extreme weather and climate calendar out this year, and so while we're waiting, I'll post another link in the chat just so people can potentially find that if they're interested in it. This will be the final year of this calendar, so it's a bit of a limited special edition. By the way, I'm looking at the publisher's website right now. Looks like there's a 20% off code this weekend or the next week for Father's Day if you use the code DAD24, DAD24 for 20% off. Let's see here. Let me just add a direct link to that in the comments, and that's my extreme weather and climate page-a-day calendar. The negative reviews on Amazon for this calendar from last year's version, by the way, folks might find this entertaining as there aren't pictures because this was actually quite an extensive research endeavor. Each individual entry was researched and fact-checked, so effectively like 212 mini essays, because that's how many calendar days there are. Different entries there are for the year. Weekends are combined, so it's not the full 365. But still, a lot of weather trivia, physical science explanations, and other fun stuff that folks may be interested in. Okay, not too many questions about the warming spike. Actually, just one, really, so I'll take a look at this one. Does global warming cause more vertical cloud and storm convection, and is that a feedback loop for global warming, since vertical clouds probably cause less shade than horizontal clouds? Another really insightful question. This has actually been an active area of atmospheric science and climate research for decades, and it is not fully resolved. In fact, we continue to get answers that conflict each other a little bit. One of the most important things to understand about clouds and climate change is that different clouds in different places have different effects. So you can have some clouds that greatly exert a cooling effect if they occur at the right altitude and in the right place on Earth. So if you have high altitude clouds in a place that gets a lot of sunlight, for example, you tend to reflect a lot of incoming sunlight before it enters the lower altitudes of the atmosphere, and so that exerts a net cooling effect. So cirrus clouds will often cool the Earth if they're in the right place. But if you have a bunch of I guess even this is complicated because you can also, for example, have marine stratocumulus clouds. These are essentially, Californians are very familiar with marine stratocumulus because it's essentially the marine layer. If it's not fog, it's essentially marine stratocumulus, that May gray June gloom. As long as it's not misty in front of your face, but it's a higher cloud layer, that's usually marine stratocumulus. These are clouds that exist within marine layers across subtropical ocean regions globally, and they tend to reflect sunlight even though they're at lower elevations. So even though it's a thin layer of clouds, they tend to prevent a certain amount of warming by their prevalence, and they're quite prevalent across the subtropical cool ocean regions near the upwelling regions, speaking of upwelling globally in the subtropics, in all of the ocean basins globally. There's some concern that in a warming climate, the marine stratocumulus at a certain level of warming might rapidly start to dissipate. That would be an example of a positive or self-reinforcing feedback for global warming through clouds. So if you suddenly got rid of a bunch of that marine stratocumulus in the subtropics, you would see even faster warming because more of the sun's energy would be making it to the surface in the subtropics. But it's unclear the level of warming where that feedback might kick in. That's one question. Essentially with convection, with deeper convective clouds, of course, say a thunderstorm, where you have clouds all the way from near the surface, just a few thousand feet above the surface at the base of the cumulonimbus cloud, all the way to the top of the cloud, the overhanging, the glaciated, the ice crystal cloud, the cirrus cloud. So you have a mix of clouds, and so different parts of that cloud are having different effects on the radiative profile, or the amount of sunlight that is or isn't reflected or absorbed at different levels of the atmosphere. So that ends up becoming complicated. It also matters the time of year and the seasonality. If you have more or less clouds, for example, over the Arctic in winter, it essentially doesn't matter in most cases in terms of sunlight because, well, there's no sunlight in the Arctic or the Antarctic, respectively, in the winter months. But if you have low-level clouds in the Arctic, that can be important because what that can do is it can insulate the lower levels of the atmosphere and prevent some of that loss of infrared radiation energy to space, because some of that infrared emission from the Earth's surface is captured by these low-level clouds and absorbed and then radiated, of course, back down toward the surface of the Earth. So the long and the short of it is there's been a ton of research on this, and the effect of clouds on climate change very much depends on the altitude of the cloud, the phase of the cloud, whether it's liquid water versus solid ice, the location and the season of the cloud. Right now, there's evidence that marine stratocumulus could be a positive feedback. So if we lose that stratocumulus, that the Earth would warm by an even greater degree. There are other places where we could add clouds or subtract clouds, and we'd actually have a net cooling effect. So it really does depend on the context. Right now, the best estimate of the net effect is that there might be a small positive feedback from clouds, so a net warming effect, although not huge. But even that is subject to considerable uncertainty because it's a mishmash of positive and negative feedbacks across all of these different cloud types, across all of the different regions and seasons on Earth. And, importantly, climate models don't represent clouds all that well. They're relatively coarse in resolution, and so we have to make a lot of approximations known as parameterizations when it comes to clouds, and those don't perfectly emulate the real world. So suffice it to say that clouds are super important in the Earth's overall radiation balance in terms of how much energy is retained or emitted back to space. They affect the efficiency of the greenhouse effect overall, and the spatial and the vertical distribution of those clouds is integral to just what the actual net effect is. It can go either way. It's an active topic of research, and there is the potential for there to be a self-reinforcing warming feedback if we lose certain clouds, especially those that marine stratus, in some ways the most benign clouds on Earth, that the coastal marine stratocumulus, that marine layer clouds across the cooler subtropical ocean upwelling regions, potentially represent a pretty powerful thermostat on Earth's temperature. This has been a recent discovery over the past decade or so that is ongoing today. All right, well, thank you, everybody. I think this has been another interesting and well-attended session. And I will probably see you all again next week. So thanks for joining, thanks for the good discussion, and please do subscribe to the channel. Again, we're looking to grow the channel this year. There may be some more announcements forthcoming, but we'll see how that goes. But subscribing and sharing is a really easy way to support the channel as well, so I would encourage you to do so if you have found these live office hour sessions worthwhile. So thank you as always. Have a good weekend, and see you next time.